All right, welcome to this course on engineering mechanics, dynamics. You took engineering mechanics statics last semester in your MEE 205, and this semester you are going to be taking MEE 206, which is the dynamics aspect of the statics you took last semester. So before going to the course, I would like to explain few things to get us started. Now we know that mechanics is divided into statics and dynamics. And the first thing is, what is mechanics? All right, mechanics is the branch of physical sciences that is concerned with the state of rest or motion of bodies subjected to the action of the forces. So if you pay attention to what I've just said, I said mechanics deals with bodies at rest or in motion and also the forces that is subjected to the body. Now, if you pay attention, two things are important in the definition. There is motion, and there is forces, Okay, those two things are important. Now, statics in 205 or last semester, the governing equation for statics is Newton's first law. Which I've written here, summation F equals to 0. We know that Newton's first law simply talks about the resultant force acting on a particle being equals to 0, or we can also say that the acceleration is equals to 0. In a simple term, by just simply saying that the body may either be at rest or may be moving with a constant velocity. And you know that when velocity is constant, you are going to have acceleration to be 0. So Newton's first law is what governs our statics, summation F equals to 0 and summation M equals to 0. That's moment. Where linear acceleration is 0, angular acceleration is also 0. But in dynamics, of course, I repeat, statics deals with equilibrium of bodies under action of forces, and the body may be at rest or may have constant velocity. All right, may be at rest or may have constant velocity. But dynamics deals with the motion of bodies with acceleration. Dynamics deals with the motion of bodies with acceleration, or we can simply put that dynamics deals with accelerated motion of the body. But dynamics is divided into two. Dynamics is divided into two. We have the kinematics aspect, and we have the kinetics aspect. Now remember I said these two equations are the governing equation for dynamics. So how can I relate those two equations to kinematics and kinetics? It's very simple. So I'm going to write the equation out here. Let's say summation F equals to MA. All right. Now, the right hand side that talks about mass times acceleration, which is motion, is the kinematics aspect. You see, don't need to cram it. Then the kinetics talks about the left hand side, the part that talks about the force. So, what do I mean? I'm simply saying that kinematics deals with or treats the geometric aspect of motion, such as your position, the velocity, the acceleration, and time. That's kinematics. While your kinetics deals with the force aspect. So while kinematics deals with the aspect of motion, kinetics deals with the analysis of the force causing the motion. Look at it this way. When a body is moving, if you are considering the position of the body, all right, or the kinematics of the body, you are simply talking about the acceleration, the velocity, all right, the time in space, everything like that, that talks about the motion of the body, or anything like that that can use to define the motion of the body is the kinematics aspect. But you are not taking into consideration the force that is causing the motion, That's kinematics. If you are going to talk about the force that is causing the motion, that is this motion now, the force that is causing it, that is kinetics. You get it now? So, and I'm going to tell you something at the end of this lecture, which I would want you to keep following. Now, we move into the next thing, rectilinear motion of particles. Rectilinear motion of particles. Of course, from the name rectilinear, recti, straight line path. Recti, straight line path. Now, in this course, whenever you hear the word particle, what I want you to know is that we're talking about a body that has a compact mass, all right? That after a time, the mass is not changing, irrespective of whatever the body may be. Insofar as you hear particle, it means that the mass is constant. The mass is constant. There is something again I want you to realize. In statics, the major thing that differentiates statics and dynamics is time. Because remember that while we are talking about statics, we never mention anything about time. In statics, we never mention anything about time. We never mention anything about time. But in dynamics, we are going to be doing, we are going to be talking more about time. Yeah, because that's what makes the difference. That's what makes the difference. So we move directly into rectilinear motion of particles. Rectilinear, rectilinear, rectilinear motion of now from the name recti, recti means straight line, straight line. Now, I've told you before, I said kinematics deals with the geometric aspect. Now, look at it this way. If you want to define a particle in space, let's say this is a particle, this particle is in space. To define this particle in space, you can't just define this particle from anywhere. Okay, you need a reference point, and that's known as the origin. So let's say this is the origin of this particle. This is the origin. So let's call this particle P. Now, when this particle, so let's say the time at the origin is at 0, and at this particular position, the particle is at time t. Now, this particle has moved, let's say the position of this particle at this particular time, let's call it S1. All right, so let me define the coordinate of this particle now. So let's say this is x coordinate, x coordinate. Now, at another time, this particle moves to another position. So let's call it t plus dt. Now, the distance moved by this particle at this particular time now is, let's call it S2. S2. Let's call it S2. Now you can, if you realize that we have now defined the position of this particle at different positions, but something is common to them. We are defining them from the origin. We are defining them from the origin. So according to our knowledge of coordinate geometry, we know that we have to define our axis. So this is our positive axis, and this is our negative axis. That's our positive axis, and this is our negative axis. Now, it is possible for this particle to move towards the right, or for it to move towards the left, or it is possible for me to take the distance of my particle towards the right, and I can also take it towards the left. But something is very important, that for us to define this particle in space, we needed to choose a fixed origin O, all right, along a straight line. Then we took this particle towards the right. According to my definition here, that means positive. Positive. If I take it to the left, that's negative. So it means that my particle in space can either be positive or negative. That is, the position of a particle in space can either be positive or negative. Therefore, position is a vector quantity. Remember, it can either be positive or negative. Therefore, position is a vector quantity since it has both magnitude and direction. Position is a vector quantity since it has both magnitude and direction. What I'm trying to say is that at the time, I was from the origin, my particle, oh, sorry, here is, let's call this P prime. It was at P, and this is the position in time, S1. Then, that's it. Then it was at this position now, T plus dt, and that was S2. So you can see that I move towards the right. Then my position, because when I move towards the right, it's positive. When I move towards the left, it's negative. Then my position is a vector quantity because it has both magnitude and direction. But to make it um, quite relatable, from your knowledge of MEE 205, how do we define position vector in statics? How do we define position vector in statics? Remember, this is the example. This is the example. This is where we used to define it. Okay, so let's say we have this coordinate, rectangular coordinate. So let's say this is z coordinate, this is x coordinate, and this is y coordinate. Let's say we have a point P in space, and because it's in space, we define it by x, y, z, x, y, z. A position vector from the origin, a position vector from the origin, that's r. Now let's assume that this particle now moves to another position in space. So this is now, let's call it P prime with the coordinate system x prime, y prime, and z prime. The position vector, again, from the origin, you see that we define an origin. We define an origin. That's exactly what I was trying to explain in this previous diagram. The necessity of defining an origin. Now, the difference in the position, that is the final position and the initial position, to get that, we're going to draw a straight line, and we call that delta r. We call that delta r. Now, you know that this particle, oh, this is r prime, all right, the position vector for this second position, or let me say the final position is r prime. Now, you know that this particle has unit vector along the x, y, and z coordinates. All right, the unit vector along the y coordinate is zk. Of course, the unit vector along y coordinate is k. Unit vector along x coordinate is xi. The unit vector along the y coordinate is yj. Now, since it is a vector quantity, we know since a vector quantity, it has magnitude and direction. And position vector is a function of time. All right? Position vector is a function of time. So what is the value of this delta r? Delta r is going to be r prime, that's final minus initial. You know that, final minus initial. Delta r is going to be r prime minus r. That means the position vector of the final position minus position vector of the initial position. So if I'm to define my r is going to have, because it is in space, it's going to have coordinate system, or it's going to have axis along x, y, and z. So xi plus yj plus zk. All right, that's my r, and it is a function of time. It is a function of time. So you can see that position is a vector quantity, and you can see that to define position, you need magnitude and direction. You need magnitude and direction. So that's how to define a position of a particle. You need a reference plane. Now, we move to the next. We're going to talk about displacement. 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 Okay, so what's displacement? Displacement of a particle, of course, we are using one particle. I'll slide down. Displacement. We are still using one particle. So displacement displacement. So the displacement of a particle, is defined as the change in its position. All right, that's the change in its position. Change in its position. Change in its position. So let's refer back to the particle that we used the other time. Let's refer back to the particle. Now you can see that for this diagram here, when this particle P was at the final position, all right, we call it S2. When it was at the initial position, we call it X1. So the change in final minus initial, that is the displacement. The change in the final minus initial, that is the displacement. Okay, so I'm going to take it down again under the displacement. Okay, so final minus initial, that's delta S equals to S2 minus S1. All right, so that you can easily reconnect. Let me draw the diagram here. We have something like this. We have our origin, then we have our particle at its first position. This first position, it was at S1. Then from origin again, we take the final position of the particle. You must always have an origin. You must always have an origin. So that's S2. Okay, so the difference between the final and initial, this is this place, here and here, that's delta S. That's the displacement. Displacement, that's delta S. That's S2 minus S1. Okay, now you need to understand something again, that I defined coordinate system when I drew the previous diagram. I defined coordinate system. I said towards my right is positive and towards my left is negative. You have to understand that this is very important for any vector at all. If you are solving anything under vector, you must always define the position. So in this case, it means that my displacement can either be positive or negative. And whether it's going to be positive or negative, it depends on the final position of that particle. So I'm trying to say that, let's assume that I have, this is the origin. Let's assume that initially this was the position, let's call it S1. If the final position moved, don't forget that I've defined this as X and this is positive. So if my displacement is going to be positive, if the final position of this particle moves towards the right, then my displacement is going to be positive. Okay, but if this final position is towards the right, if the final position were to move to the left, that is the left hand side of this initial position, let's call it S2. If it were to move to the left, don't forget again, it is final minus initial, then my displacement will be negative. So the displacement of a particle is a vector quantity. Do you get it now? It has magnitude and it has direction. And displacement is not the same thing as distance. Displacement is not the same thing as distance. Let me give you an example of the difference between displacement and distance. Let's say a particle covers a distance at a particular time. Let's say I have, this is my origin. So let's say this is my origin. And let's say the particle was at this point, let's call it P, at this particular time. And this particle is now at this position, P prime, at this other time. So you know from the origin, I'm going to take it, this is going to be the delta S. It's going to be delta S. So this is it. If this particle moves from the origin, and okay, let me not use this diagram. I'm coming back here. Let me use a simple diagram. Let's say this particle here moves from the origin like this and comes back to its original position. All right, moves from the origin, then comes back to the original position. Now, the displacement of this body is 0. Why? Because it didn't change position. That means you started from the same point and you ended at the same point, just the same way we used to talk about in energy, that you may be carrying a block on your head, insofar as you are not working, all right? And you may be sweating, no, but you have not done any work because it is force times distance. Your distance is zero. Even though you are sweating, you have not done any work. Same thing applies to displacement. You started at a particular point and you are ending at that particular point. Okay? That means your final minus initial, 0 minus 0, because that's the origin, equals to 0. So your displacement is 0. For the distance covered is the magnitude of displacement. Distance is the magnitude of displacement. That's the magnitude of displacement and is usually positive. So how do I calculate the distance covered? The distance covered is the total length of path that this guy moves or that this particle moves. So it moves like this and like this. So don't forget, I said the total length here is 5 meters. Let's say this total length is 5 meters. Okay, so this particle actually traveled from here to here is 5, then traveled back to the original position, that's 10. So total distance is 10 meter, but displacement is 0. Why? Because you started from a position and you are ending at that same position. So distance is the total length of path over which the particle travels. Distance is a scalar quantity, while displacement is a vector quantity. The same way you're going to talk about when I get the speed and velocity. Okay, so that's the difference between displacement and distance. Then we'll move to the next definition of term under our rectilinear motion, which is velocity. I'm going to tell you something at the end of the video because the course can be overwhelming due to a lot of formulas, but I need to give you a hint as to how to go about it as we go on. Now, velocity, the next definition of term. Don't forget, I said that for you to know the position of a particle in space per time, you need the velocity, you need the acceleration, all right? You need the displacement, all right? So that's why I'm trying to define this terminology. So what's the velocity? Now, you see, if this particle, the same particle we are talking about, I will still draw it again. If that particle moves through a displacement, delta s, if that particle we are talking about moves, let me go back. If that particle moves through a displacement of delta s during a time interval of delta t, so let me show you something. Uh, Look at this diagram here. You can see that in this diagram, we are simply saying that this particle at P prime, final position. So if it moves a distance of delta F, oh, I've not written that here. So we know that this is delta S, difference between its initial position and final position. Okay. So we're simply saying that if this particle actually moves a displacement delta S at a time interval of delta T, all right, this dt here, you can also say it is T plus delta T. Okay, still the same thing. All right, the average velocity of the particle during this time interval is given as delta S divided by delta T. Let me go back to average velocity. So we are simply saying that our average velocity for this particle, that's velocity average, come on my pen, velocity average is equal to delta S over delta T. That's our average velocity, which is something as S2 minus S1 over T2 minus T1. Let me show you how I go that. So look at this particle at the top. Look at this particle. So at the final position of this particle is having T plus dt. It's having T plus dt. So if I want to call it for easy notation, I can say that let me call my initial position T2. Based on the notation I've used, let me call my initial position T1. So what we are doing as to our average velocity is that we are saying my final position, that's S2, it has covered a distance of S2 from the origin as final, minus its initial position is S1 from the origin. Then my final time is T2 minus T1. That's what we are trying to say. That's going to be the average velocity of that particle. Now, if we take smaller and smaller values of delta t, that is, as delta t approaches 0, consequently, we are going to get what we call the instantaneous velocity. All right, the instantaneous velocity is given by our instantaneous velocity v is given as the limit as delta t tends to 0, then we're going to have delta s over delta t, which is same thing as v equals to ds dt. That's as delta t approaches 0, we're going to get our instantaneous velocity. Now, again, I discussed about displacement and distance and their difference. Same thing applies here, velocity and speed. The magnitude of velocity, that is the magnitude of velocity v, is speed. The magnitude is speed. And we used to use the term average speed. Again, average speed is always positive, all right? Average speed is always positive. It is also a scalar quantity. Our velocity is a vector, our speed is a scalar. Now, how do we define our average speed? Our average speed is actually the total distance traveled by a particle divided by the time interval. What I'm simply saying is that if our particle moved from its initial position to its final position, the total distance traveled, that is, it's just like the same we said the length of path under distance. So in this case, total distance traveled. Now our average speed is represented as s subscript t. All right. Sorry, I mean v average. Then we have average. So this is average, this is speed, this is SP here. SP here. So if my particle was here initially, and the particle is now here, I'm coming. Particle was here initially, then my particle is now here. So we are simply saying that the total distance, or let me say the length of this path, yeah, the length of this path, that's our ST. All right, that's the total length of path. So our average speed, our average speed, our average speed. So sorry, our average speed v speed average is total distance over the time interval. Total distance traveled over the time interval. Don't forget, it is a scalar quantity and it is positive. All right. Now, the next thing we want to define now is, let me ask you a question. We know that if, okay, so I do not want to make it in terms of question for now, but let me just say, now average speed is also something as speed, and it is the magnitude of velocity, and it is positive, right? While average speed is positive scalar, average velocity can be negative. Average velocity can be negative, can be positive. Okay, that's something I want you to really see there. Okay, that's something I want you to really see. Now we move to the next definition of term. We have acceleration. We have acceleration. Now, we are still using the same particle we have been using in this, our explanation. We are still using the same. Now, acceleration now, provided that the velocity of the particle that we are dealing with is known at 2 points, the same way we need the displacement at 2 points. Now, this time around, provided that we know the velocity at 2 points, we can get what we call the average acceleration of the particle at a particular interval. All right, velocity was the time differential of the displacement. All right, the rate of change of time with respect to what the displacement. While our acceleration is the rate of change of time with respect to velocity. So we can have our average acceleration to be defined as delta V over delta T. Delta V over delta T. That is, we're talking about, we can have V2 minus V1 over T2 minus T1. That's what we're talking about, this possible. That's the difference in velocity during the time interval of this delta T, the difference in velocity. And let me show you something. Let's say this is our particle at time T. This particle moving towards the right, that's positive. It has the velocity of v. Then at another time, t plus dt, this particle can be moving with, this is now, the particle is now p prime, with the velocity of v plus delta v plus delta v, or you could call it v prime or v2, whatever. So our delta v is going to be v prime minus v, which is the final velocity minus the initial velocity at a particular time interval delta t. All right, the delta t is gotten, of course, you know, this also can be t plus delta t. So if I'm to do final minus initial, you know what that means? So it's going to be v prime minus v prime minus v all over, then if I say t plus delta t minus t, so this will go, all right. Then if I want to bring my v prime as v plus delta v, you know that v will go, so I'll be left with delta v. So that's how this was gotten. Now, we move to the definition of instantaneous acceleration. If you take smaller and smaller value of delta t, if you take smaller and smaller value of delta t, and the corresponding value of delta v, we are going to have instantaneous acceleration, giving us the limit as delta t tends to 0. We're going to have delta v over delta t, which is same thing as the v dt. That's our instantaneous acceleration. Now, I don't want to make the lecture too long. I do not want to solve some problems here, but I need to make a statement. Okay, now you know that v is dS dt, and we know that a is dv dt. Okay, a can also be expressed as, if this is d dt and I put ds dt, so I'm going to have d square s over dt square, d square s over dt square. So both average and instantaneous acceleration can either be positive or negative. They can either be positive or negative. I'm going to give you one example before I move on. I'm going to explain this more with a question. Why they can either be positive or negative. That's both average acceleration and instantaneous acceleration. You know that we have defined this as the positive. I have defined this as the negative. This as the positive and this as the negative. You know that if a car is speeding up in this direction, our acceleration is going to be positive, all right? But if a car is reducing its speed in this direction, you know what I mean? That you are reducing your speed. It is possible that you're moving towards this direction and you are reducing your speed, then acceleration can be negative. Okay? Acceleration can be negative. Same thing that you used to call deceleration. Okay, now I said it from the beginning of this lecture that dynamics can be overwhelming. Dynamics can be overwhelming, and there are a lot of formulas that you are going to be needing along as we solve this problem. But I think you don't need to cram any formulas in dynamics. You do not need to cram any formulas in dynamics. There are major formulas that you should know to heart. That is, you should be able to recollect at any point in time. And if you can recollect these formulas, you can easily work your way through to get all other formulas. And I'm going to give you those four formulas. All right, so there are majorly four formulas you can use, you should know that you should be able to easily recollect. The fundamentals, we have V, number one of it is V equals to ds dt. Number two, we have our A equals to dv dt. Number three, cos, everyone should be familiar with this from your basic knowledge of physics. And this one, SR theta. Of course, you know that this one is nothing. This is our theta, and this is our radius, and this is our s, and the length of the arc. All right. So I believe that these are the four formulas you should be able to recollect at any point in time. If you know these four formulas, you can easily use them to recollect all other formulas you need. For example, if you combine 1 and 2 together, that is, if you combine equation 1 and equation 2 together, you can get the third dependent kinematics equation. These two are independent, but the third one is dependent. So we can get something like this. If I combining 1 and 2, I'm going to get dt equals to ds over v. Okay? The same thing equals to dv over a. So if I cross multiply, I'm going to have a ds equals to v dv. So you can get the third kinematics equation, although this one is dependent. Okay, now this is possible. Now, if you now take this newly derived equation, this equation that we have derived now, if you combine it with equation 3, if you combine this with equation 3, you're going to have something like this. You know, it is F equals to F equals to MA. Okay, now if I have DS here, DS here. What I did is left, I also did to the right. You know that MA, this ADS is same thing as VDV. So I'm going to have MVDV. I'm going to have MVDV. Okay, then if I integrate the left hand side and the right hand side, that is, if I integrate this one and I integrate this one, I'm going to have my lower limit, my upper limit, f ds equals to integral of my lower limit, my upper limit. Of course, you're going to take mass outside. I'm going to have v dv. By the time you are done integrating, you're going to get half mv2 squared minus half mv1 squared. All right, this formula is the principle of work and energy. All right, you're going to meet these formulas as we go ahead in this course. Principle of work and energy. Principle of work and energy. Okay, so that's on that. Now, if I combine, I'm just trying to tell you some of the formulas that you can get that you don't necessarily need to cram. Insofar as you know the major formulas, you can just walk through it with your mathematical knowledge and just derive the rest. You can be certain that if you are deriving it, you won't make mistake of putting two things or exchanging values. Now, if I combine, 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 don't mind my pen, if I combine A equals to dv dt, all right? If I combine it with this one, F equals to ma, you know that F is equals to mass, then acceleration is dv dt. You're putting your acceleration in the place of this acceleration. All right. Then if you cross multiply, you're going to have F dt equals to m dv. Then if you take the integral of both sides, you're going to have the integral, of course, you know, at your initial time, lower limit, upper limit of your F dt equals to, lower limit is v1 and upper limit is v2. Of course, n is going to come out v2. So you're going to get this mv2 minus mv1. We should be familiar with this formula in our basic knowledge of physics, which is under momentum. Of course, you know momentum m1 v1, m2 v2 minus m1 v1. That's what we have just derived here. Okay, so if that be the case, you see that combining those two things at the top here, we have been able to get this one, which is the principle of linear impulse and momentum. This is it. You see this formula will be applied as we go on. Principle of linear impulse. Principle of linear impulse and momentum. And momentum. Now, we can also combine, if you combine the four equations, that is the four equations I gave you at the top, you can get this omega equals to 3 theta over dt, which is same thing as v over r. Of course, our angular acceleration give us the omega dt, which is same thing as our tangential acceleration over r. And then you know that alpha d theta equal to omega d omega. So we can get many other formulas from these guys, and I'm still going to walk you through them as we get to this each of these topics. So dynamics can be overwhelming, but you should not focus more on cramming. You should not focus more on you want to cram and just get this example and go. No, understand the basis, understand what each question is trying to say. And maybe in the next video, I'm going to explain. In the next video, I'm going to explain the tricks, or let me say the hints that you can follow in answering questions in this course. Thank you for this lecture. See you in the next lecture.